Hello everyone, we are Group 8. Today we will be presenting on the hash aggregate operator. We will begin by discussing the hash aggregate algorithm with examples, followed by complexity analysis, memory consideration, and spilling. Then we will demonstrate the operator using both sorted and unsorted data, comparing the stream aggregate and hash aggregate operators. We will also work through the query plan and memory consideration. Finally, we will conclude the presentation with a summary. An aggregate is a function that computes the summary values such as sums, counts, or averages over a set of grouped data. There are two types of aggregation, stream aggregation and hash aggregation. Stream aggregation requires the data to be sorted by the grouping column before we start scanning it. This method processes one group at a time. Sorting is expensive, so stream aggregation is used only when necessary, such as when the data is already sorted by an index or when an order by clause is used. Hash aggregation, on the other hand, does not require sorting the input data. It is more efficient for unsorted data and works by using a hash function and a hash table. For each row, we apply a hash function that tells us to insert a new row in hash table or update an existing one. Then at the end, we scan the hash table to get the results. So there is no sorting is involved, just the hashing. The algorithm relies on hashing the input rows based on the group by columns. So for each input row, the hash function check for matching row in the hash table. If there is no match, it insert a new row in the hash table. If there is a match is found, it updates the matching row with the new data. And lastly, it outputs all the rows from the hash table after processing the entire input. This means that hash aggregate can compute all the groups simultaneously, unlike stream aggregate, which computes group one by one. So let's see what the algorithm looks like with an example. We have this table. It shows a set of sales data with two columns, region and sale amount. Each row represents a sales transaction from a specific region, and the amount indicates the sales value for that transaction. We write this query. The query selects the region column to group the data by each region. It calculates the sum of the cell amount for each group using the sum function and analyzes the result as total sales. The data is pulled from the sales table and the group by region clause ensures that the sum is computed for each region separately. We begin with hash table and hash function to group the data. The process involves scanning through each row of the table, calculating the hash for the region sales amount, and inserting or updating the corresponding row in the hash table. So in first step, it start with the not region. The hash function will either insert a new row or update an existing one in the hash table. Since hash table is empty at first, not is inserted. Then we move to the south and apply the same process. It is also inserted into the hash table. Next, we process east, which is inserted as a new row in the hash table. When we encounter north, again, the hash function finds the existing row and updates it, adding the cell amount. The same happens with the east. The existing row is updated, and West is inserted into the hash table as it is new. And for the south, it is the same. So there was a existing row for the south. So the south sales amount is updated. Once the hash table is populated with necessary values, we simply scan it and output the unique regions. The result doesn't follow any specific order as the hash table does not impose sorting. Let's walk through another example with the given table and this query. The query selects the region column and calculates the average of the cell amount for each region using the average function. The result is analyzed as average. The data is pulled from the sales table and the group by region clause ensures that the average is computed for each region individually. We start by using the hash table and hash function to process each row. For every row, we not only compute the hash for the region, but also two key pieces of information, the sum and the count. The sum keeps track of the cumulative cells for each region, and the count tracks how many times the region has been encountered. So, in the first step, uh, we start with the north region. We calculate the hash value and insert it into the hash table. At this point, the sum is 100 and the count is 1, since it is the first occurrence of the north. Then we process the south. So it is the first time we see the south. So the sum is 200 and the count is 1. And for the east, the sum becomes 150 and the count is 1. And then when we encounter north again, the hash function identifies the north already exists in the hash table. We update the existing entry by adding new cell amount to the sum and incrementing the count by 1. And the same process happens for the east of and the east region value, the cell amount is updated and also we increment the count by 1. And the west, and for the west, it is new to the hash table and we added the hash table with a sum of 300 and count of 1. And for the south, it is existing, it was in the hash table. So we update the cells amount and the count, increase the count by 1. So now the count is 2. After all rows are processed, we scan the hash table. For each region, we calculate the average by dividing the sum by the count. This will give us the final result. So this explanation covers the theory, but in practice, there are additional considerations like hash table size, memory limitations, and whether the table can fit into the memory. So now here comes the runtime complexity. So the average case runtime is big O of n, where n is the number of the input rows. The average runtime is linear in relation to the number of rows n, as each row requires only a hash computation and a lookup in the hash table. For the worst case scenario, it is big O of n squared. The worst case time complexity arises where when there are hash collisions, which leads to increased lookup times. However, most modern hash table implementations ensures constant time complexity on average for these operations. It makes hash aggregation efficient for large data sets.
Now on to the topic of memory and spilling. Now, generally speaking, the hash aggregate algorithm calculates the hash values on groups by columns, while it checks for matching rows in the hash tables. To clarify, suppose there is one row stored for each group, and you have a larger number of unique values within these groups within the hash table. So then you have more rows being stored consequently, which takes up more memory. And the reason why this is important is because In the query plan, a stream and a hash aggregate may appear the same. The latter is much more cost intensive due to the memory requirement, which is actually proportional to the number and size of the output groups or rows. Now, conversely, suppose you have many duplicate values inside the group by columns or the number of groups. So, in this hypothetical scenario, because more rows are matching within the hash values within this internal hash table, the hash aggregates become incredibly efficient, which, while it's more uh, expensive in terms of the cost computation, it becomes becomes much more efficient over queries that process much larger data sets or work with much more data. And partially how the query optimizer decides to choose between stream and hash aggregate is based off a cardinality estimate, which is an estimate based on the total number of rows which are processed at each level in a query plan. That's a general overview. I'm not going to explain incredibly too much in depth for the sake of time. Now, on the topic of spilling, if the memory requirement is too large, if you look in the actual query plan, you'll see that hash aggregates being displayed with a warning sign. This shows that there was a spillage. And what a spillage is when memory runs out and it begins spilling rows into temp DB, which is onto the disk. The query engine uses memory, so data such as multiple buckets, partitions, or partially aggregate results. They're spilled into these additional new rows, which are then hashed into spilled buckets or partitions. These new spilled rows are hashed and divided among several buckets and partitions. And it's important to also mention that hash aggregates are known as a blocking operation, which means that it doesn't produce any output until everything has been consumed. So back onto the topic of discussion. Once all the input groups are processed, the complete in-memory groups are then output. And in order to save more memory, this algorithm repeatedly reads back and aggregates the spilled partition every time. And since these aforementioned new spilled rows that were created, they aren't aggregated, but they're instead hashed and divided into several partitions, which means that overall um, the size of the partition is reduced incredibly so, just to save memory, as hash aggregates are memory intensive, and when it spills onto disk, it's important to divide that up into several partitions. And here is a demonstration of how hash aggregate works. You have the input, and then this is the internal table, which memory is stored proportionally to the number of rows, and it's split, and then it's then aggregated back. Um, if you see here in the sums, uh, and based on the hash values, and it's combined again.
This is the demo for Hatch Aggregate. I create a database named Aggregate with 4 tables in there. The first table called student grades sorted with the 1200 rows of the data in there. The primary key is on student ID and course ID. The second table called student grades sorted 1 with 400,000 rows of the data in there. The primary key is on student ID and course ID. The third one called student grade unsorted with 1200 rows of the data in there. This is unsorted data, so it has no primary key or indexes at all. The last one called student grade unsorted one with 12,000 rows of the data in there. This is also unsorted data without primary key or indexes. Why we have to learn about unsorted data? Because there's a lot of data out there in the real world which is unsorted or too expensive to sort it. So the query optimizer try to find the cheapest way for us to work with all of those database. Um, from here, the hash aggregate is actually good for the unsorted data, But sometimes users will like, will the query optimizer choose to use hash aggregate with the unsorted data all the time? I can show you in this demo. For the basic aggregation, like count, find the minimum, maximum, average, or summation. For the sorted data, you can tell they have like the cluster index in there. What you can guess like what the query optimizer will choose as a query plan for you. When you take a look at the query plan of the sorted data here, you can see that they choose the optimizer will choose to use the stream aggregate for you. With use the cluster index scan for the whole table, and do the stream aggregate. But for unsorted data here, when you do the like work with the unsorted data and you take a look at the query plan, the query optimizer actually choose to use the hash aggregate for you, which is create the hash table of first do the table scan and do the hash table for you. If you click on here, you can see that for the hash aggregate, the property here, you will see the memory fraction here. That means for the create a hash table, you actually need the extra memory to create a hash table. But if you go back here a little bit to see the sorted data, the query optimizer, sorry, the query optimizer here will show the stream aggregates for you. When you click on here, you actually don't see that you need the extra memory here. For this is when you try to do the average of the grade, grouped by the student ID. uh, if you run this one, because this data is already sorted, when you do the execution, is the student ID will sort it for you already. But for the hash, for the unsorted, which is you use the hash aggregate, when you do this one, run it, is actually is not guarantee the order. It's just group by the student and then do the average of the grade for you. Don't guarantee is we sorted or do the order for you. So but if you want the result with the order by student ID, for this one, maybe you can guess, because it's actually the table is actually sorted, or has the primary key on student ID and course ID already. So this one, if you guess, is the query optimizer should choose the stream aggregate for you, because it's cheaper anyway. So if you click on that, you can see both, even those big data or smaller data. This one has, the first one has 1200 rows, the second one has 400,000 rows of the data in there. Both will use the same thing, do the cluster index scan and then do stream aggregate for you. But for unsorted data, this is the one that we really interested in for the for this demo. When you do, can you guess like, because is try to call order by student ID. That means you want the result is sorted for you. So for the query optimizer, we'll try to find a way, which way is cheaper, sort it first before do the operation, before averaging, or um, do the hash table, do the average, and then sort it for you later. The for the upper table here, we'll have 1200 rows. For the lower table, we'll have 12,000 rows. which is 10 times of the data in there. So now we will see what query optimizer will choose to use for us. From here, you can see, oh, okay. For the first one with 1200 rows of the data, the query optimizer actually do the sorted for us first. Do the sorted on the student ID first before do the stream aggregate here. But for the second one is bigger data. When you don't want to sort the whole 12,000 rows before do the average. You actually want to spread it or create a hash table and then sort it at the end, because once you do the average already, the rows that you have to sort it is actually smaller, kind of like you want to sort it as less as you can, because it's expensive. If you have enough memory, this one is actually will do the hash match, the hash aggregate for you. If you click on here, you can see they have the memory fractions there for you. And this one, okay, you don't need the extra memory. If you run this one, if you actually run or execute this one, you will see here in the property, you don't in the property you don't see the extra memory at all. But when you run this one, we use the hash aggregate for us. When you click here, you can see that for the hash key build here actually need the memory usage here. I will try to show all at once so then you can see the difference here. Okay, this is all. This is for the sorted data. When you want the result that ordered by the student ID, both sorted data, which the query optimizer will choose to use stream aggregate for us. But for the unsorted data, the first one has a smaller data, and the second one actually have larger data. So the smaller one sorted maybe don't really cost that much different than sorted later. So the query optimizer actually choose to use sorted first and then do stream aggregate. But for the larger data, which is the in the real world, you have the big data out there. How to work on that is actually we'll do the hash aggregate for us and then sort it later. So this is the demo of hash aggregate. Now we come to the summary of hash aggregate. In SQL Server, both stream and hash aggregate are types of operators used in query execution plans to perform the aggregation operations. Stream aggregate. It performs aggregation in a single pass through the input data. Is suitable when the data is already sorted according to the grouping or columns. But for the hash aggregate, it does not require the input data to be sorted. It hashes the input rows based on the grouping columns and then aggregates the rows with the same hash value. It's suitable for unsorted input data or when the optimizer decides to use a hash aggregate would be more efficient than the stream aggregate. And this is the presentation of hash aggregate. Thank you.